Introduce Igor Kortchemski. We will talk about condensation in critical Cauchy Bienaymé-Galton-Watson trees.
Yes, thank you. Is the mic working? Yeah. No? Yes? Okay. So thanks a lot for the invitation. I'm very happy to be here to speak about joint work with Loïc Richier, which concerns condensation in critical Cauchy Bienaymé-Galton-Watson trees with some applications in random planar maps. So I'll start with an introduction. And let's say that the goal or the context in which falls this work is to understand the geometry or the structure of large random trees. And more precisely, we fix T sub n be a Bienaymé-Galton-Watson tree, a random tree, which I will write BGW, with a fixed offspring distribution, with offspring distribution mu, which is a probability measure on the non-negative integers. So it's really the simplest genealogical tree you can imagine. You start from an ancestor, and everyone has an independent number of children distributed according to mu. Okay, and this tree is conditioned on being large, on having a fixed size, on having n vertices, with n being large. And the question is, what does Tn look like? For n large. So I'll first describe some known results in two directions. First, the local limit direction, and second, the scaling limit direction. So first, local limits. In the local limit framework, you just want to understand what happens in balls centered at the root. So what happens locally in this tree when n tends to infinity. So first case, the critical case, mu is critical, mu has mean 1. Then Tn always has a limit for the local topology. Tn converges in distribution for the local topology to an infinite tree T infinity, which looks like this. It has a root, so I grow trees from left to right. It has an infinite spine. And there are outgrowths on the spine, which are independent trees. This is the so-called Keston tree, or Bienaymé-Galton-Watson tree conditioned to survive. So this is first due to Keston under a different conditioning, with very general results by Johnson and further extensions by Abraham Delmas. Now, if mu is not critical, but subcritical, and you assume that the radius of convergence of the generating series associated with mu is 1, so there's really the 1 plays an important role, then Tn also converges in some sense locally in distribution to an infinite tree T infinity star, but this time it does not have an infinite spine. So T infinity star looks like this. You have a spine of geometric length, but the spine is finite. And on the spine you have outgrowths, which are finite independent trees, but at the top of the spine you graft infinitely many trees. And this phenomenon was first observed by Johnson and Stephenson, with general results by Johnson and further extensions by Abraham Delmas. this is for the local limits. Now scaling limits.
For the limiting tree, you have balls, finite balls to infinity.
So yeah, I didn't want to enter the definition of balls in this case. So you can do a cutoff in height. You only look at balls at distance r from the root, and you keep, for example, only the r first children. So there's you have to be a bit careful in the definitions of the local distance you use, but yeah, you can make sense of this. There are other questions on this. So now scaling limits. So to write some results, I need a definition. The notion of domain of attraction of stable laws, which already appeared this morning. So just to recall, we say that mu is alpha stable, or to be more precise, falls within the domain of attraction of an alpha stable law, with alpha between 0 and 2, if either the variance of mu is finite, and in this case alpha is equal to 2, or mu has a heavy tail. It behaves like 1 over 8 to the I to the power alpha, but up to a slowly varying function, where L is a function which is slowly varying, which means that for every fixed positive t, L of tx divided by L of x converges to 1 as x goes to infinity. So typically you can think of L, the slowly varying function L, to be log, or 1 over log, or log to some power, 1 over log to some power. So now I can say, maybe I'll go over there. What happens first when mu is critical and in the domain of attraction of an alpha stable distribution. So mu critical, alpha stable, with alpha greater than 1, at most equal to 2. So in this case, we have scaling limits, distances in the tree or behave like n to some power, which depends on the alpha, and we also have a slowly varying function correction which can appear. And then we have a scaling limit. These trees appropriately scaled converge to a continuous tree in some sense, convergence in some sense, 2t alpha, where t2 for alpha equal to 2 is Aldous' Brownian CRT, which appeared this morning in Gregory's lecture. And more generally, T alpha is the alpha stable tree. And these results are due to Le Gall, Lejean, Duquesne, and subsets. Okay. Now, if mu is subcritical and has a heavy tail, critical, and the mu of n behaves like some slowly varying function divided by the n to the power 1 plus alpha. So here it's a slightly stronger regularity assumption. This assumption on the atom of mu at n implies this, but here it's a local condition which is a bit stronger. Then there is a condensation phenomenon which occurs. There exists a vertex of degree of order constant times n, and all other degrees are little o of n. And so this is something I was interested in. In some sense, in this case, the tree is subcritical, you force it to be large. What costs the less is to have a star somewhere in the tree. And this is intuitively consistent with that result, because here you have a condensation phenomenon, you have a vertex with macroscopic degree. Here in the local limit you have a vertex with infinite degree, so intuitively this is consistent. And with Loïc, we are interested in a particular case. We focus, in some sense, in the missing case alpha equal 1 here. We focus here on mu critical and alpha equal to 1. That is, you assume that the tail of mu, the on-swing distribution, behaves as a slowly varying function divided by I. And the question is, what happens in this case? So some comments. Here, you will, if you want to say something, you have to have slowly varying functions. You cannot just take a constant here, because otherwise mu would have infinite mean. And mu has to have mean 1. So you cannot escape slowly varying functions will be here, and they play an important role. So they are really part of the system. Yes?
The result for mu subcritical here, was it valid for alpha equals 1 too?
No, it's, sorry, yeah, thank you. I should have made things precise here. Alpha greater than 1, any alpha greater than 1. Yes, thank you. If alpha is between 1 and 2, whoops, mu is in the domain of attraction of an alpha stable distribution. If alpha is greater than 2, then it is in the domain of attraction of a Gaussian distribution. So here, even in the case mu finite variance, you need to have some regularity on the atom. Thank you. Yeah. And also the reason, then you could ask, okay, but what happens if alpha is less than 1? If alpha is less than 1, and this holds, then mu will always have infinite mean, so this case is ruled out. And also, we work with not Tn, but T greater or equal to n, which is a Bienaymé-Galton-Watson tree with on-swing distribution mu, conditioned on size at least n. And if we assume a stronger condition on mu, that is mu of I equal to L of I divided by I square, then we get results on Tn, the tree condition on having exactly n vertices. In some sense, here we have a tail condition, so we get results on a tail conditioning. If you have a local condition, then we get results on a local conditioning. But of course, it would be very interesting to know what happens when you only have a tail assumption and you work with a tree condition of having exactly n vertices. And here we do not know, in general, what happens. Okay, so now I can state our main result. Theorem 1, which is joint work with Loïc Richier. So let delta n be the maximal degree of the tree. So maybe I should write delta greater than or equal to n. Okay. And h sub greater or equal to n, the height of the associated vertex. So with high probability, there is a unique vertex with maximal degree. This is its degree, and this is its height, its distance from the root. Then there exist L1, L2, which tends to infinity, which are slowly varying functions, such that one, the maximum degree is macroscopic, is of order n, but as always in this case, up to a slowly varying function. So the maximal degree will not be of order n, as here. It will be macroscopic up to a slowly varying function. And once you scale properly, you converge in distribution to a limiting random variable, which is explicit. So the fact that we have a random variable here comes from the fact that we have a tail conditioning. If we have a local assumption and a local conditioning, here you will have a deterministic random variable. 2, where does condensation occur? What is the height of this vertex where condensation occurs? Divided by a slowly varying function L2, it converges in distribution to an exponential random variable. So the vertex where condensation occurs escapes to infinity. Its height tends to infinity, but very slowly. Let's say like log or something like that. So you see that here something interesting occurs, because here you are critical. So I erased the result. The local limit when mu is critical is the Bienaymé-Galton-Watson tree condition to survive, which has an infinite spine. The local limit, you have an infinite spine, but you have condensation. So how is this possible? The reason is that the vertex where condensation occurs has height which tends to infinity, so it escapes to infinity. You do not see it in the local limit, but it still is there. Are there any questions on this statement?
L1 and L2, how they're related to capital L?
Through scaling constants, which will appear later. But yeah, I can give you an example. So let's say that if you know big L, you can compute the slowly varying functions. For example, if you assume that mu of n is asymptotic to, let's say, c over log n squared times n squared, then L1 of n is log n over c, L2 of n is log n over c squared.
Can you get something else in log n time constants? Or, I mean, the fact that it's log n, do you have examples where you get something else in log n?
Yeah, if you take, if you're here, because big L is 1 over log n square, so this is, so you get here, it turns out that when you do Dehaene's inverses and so on, you get log n, but if you take another slowly varying function big L, you could get, you could get pretty much what you want, probably.
Yeah. First part of theorem 1, it seems that you're saying that the maximal degree will asymptotically be greater than n over L1 of n. Is possible? Because your random variable j is greater than 1, apparently.
Yes, but yeah, but L1 of n is very big. So if you take j fixed and you multiply j very large but fixed, and you multiply it by n over L1 of n, you still have something which is less than n.
No, that's not my point.
Sorry.
No, the fact that it is, it cannot be less than n over L1 of n.
Yes.
Okay.
It's the probability that j is at least 1 is 1. Yes. Okay. Yes, yes. The probability that j is at least 1 is 1. There are other questions on this? So my goal is to show you the first part of Theorem 1, and the main tool is the use of random walks. Because random walks code Bienaymé-Galton-Watson trees, so I will briefly explain this. So if you have a tree T, you can code it by a path, the so-called Lukasiewicz path, W of T, indexed by I, with I greater than or equal to 0, less than or equal to the number of vertices of T. So on an example, let's take this tree, plane-rooted tree, and I will associate with it a path. And the rule is that the jumps of this path are the number of children minus 1. So first I need an order on the children. So here I take the depth first search. I index the vertices according to the depth first search starting from 0. And then when I start at 0 and I look at the number of children of 0 minus 1, so it's 2. So I make a jump of size 2. Now I am at time 1. I make a jump of size number of children of 1 minus 1, which is a jump of size minus 1, and I continue. This gives me a path associated with the tree, which is in general bijection between trees and certain paths. And what is very nice is that when the tree is a Bienaymé-Galton-Watson tree, the Lukasiewicz path is a random walk killed upon hitting minus 1. So what are the jumps of the random walk? So I introduce the random walk. Let xi be iid with probability that x1 is equal to I. The probability that the random walk makes a jump of size I. It's just my mu of I plus 1 with I at least minus 1. In words, you sample something according to mu, which is the number of children. You subtract 1. And this gives the jump distribution of the random walk. And then you define the associated random walk, which is a random walk on the integers, which makes negative jumps of size at most minus 1. And I will also need the first time the random walk becomes negative, since it is downward skip free, the saying that it becomes negative, it's exactly the same as saying that it touches minus 1. Okay, so then it is well known that the Lukasiewicz path of my tree conditioned to have a size at least n behaves as my random walk conditioned on a late return to the negative axis. Here, to be really precise, I should stop it when it touches minus 1, but okay, I put it under the carpet. The idea is that you see here the first time the walk touches minus 1, it's exactly times 6, which is the number of vertices of the tree. So conditioning the tree on having size at least n amounts to conditioning the random walk on zeta at least n. Okay. Are there any questions on this coding? And an important feature is that since mu is critical, this random walk is centered. And the tail of x1 is the same as, asymptotically, the same as the tail of mu. Okay. So now I will gather some ingredients for the proof of theorem 1. So ingredients on random walks, results on random walks. So there will be two ingredients. First, the scaling constants, which will determine L1 and L2. And second, weak ladder times, which will play an important role. So first, scaling constants. Let an Bn be such that n times the probability that x1 is greater than or equal to an converges to 1. Okay. And I set Bn to be n times a truncated mean x1, indicator x1 is less than or equal to the absolute value. Sorry. I truncate x1 when x1 is large. And it is possible to see that Bn is non-positive. So these are two scaling constants. And then by standard results on domains of attraction, the random walk minus Bn divided by An converges in distribution as n tends to infinity to a Cauchy random variable, which is spectrally positive. So this is just the central limit theorem in this framework. And what is important here is that although the random walk is centered, here you have a centering constant, and this comes really from the fact that alpha is equal to 1. If alpha is greater than 1, you will not have this centering constant. And this scaling constant Bn is negative, tends to minus infinity, and is really of order n times a slowly varying function. So although the random walk is centered, it has a sort of pseudo-negative drift, but it is still centered. Okay. Are there any questions on this? Okay. So now I can introduce now the weak ladder times. So the first weak ladder time is time 0, and then for I greater than or equal to 0, t sub I plus 1 is the first time after time ti when my random walk beats weakly a record. So for example, if I take an example of a walk which starts at 0, does something like that. Here, let's say, is time n. Then, until time n, I have a weak record here, 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 here. And a very important random variable is the last weak ladder time up to time n. Let an be the last weak ladder time of W0, W1, Wn. So here, the last weak ladder time until time n is here. This is In. And this random variable will play a very important role. Are there questions on these definitions? So now I can state the results we will use on random walks. Lemma 2 you can control more or less the law of the last weak ladder time up to time n. This is the probability that zeta is greater than j times the probability that t1 is greater than n minus j. Here j is between 0 and n. 2, In is not that large. In divided by n converges in probability to 0. So proof. The proof of the first result is simply a time reversal argument at time j. So here, for example, we have time j, and you say instead of reading the walk from left to right, at time j, you read the jumps from right to left. So this means that you put your axis like that, and you look at your walk like that. And so you say that, you see that saying that j is a weak ladder time is exactly saying that this reversed random walk has not reached this level so far. So this gets you the first term, and this term just says that you have no weak ladder times from j to n. So this is time reversal at time j. And 2 is, there are many ways to see it, but maybe the simplest one is to use a scaling limit argument and say that the random walk Wn, appropriately scaled in time and space, converges to a Cauchy process. And because of this centering, your random walk will really look at something like that up to time n. Of course, then it will grow up again, but if you look at scale n, In will be very close to 0, in the sense that In divided by n converges in probability to 0. But I don't want to enter details. And now lemma 3, which is technical. So this is an important input, and it extends an estimate of Quentin Berger, which was obtained recently. Broke in 4 pieces. Okay. And so this estimate tells us that there exists lambda, which is slowly varying, such that the probability that zeta is at least n, the first entrance time of the random walk in the negative axis, it's asymptotic to big L of Bn divided by Bn times lambda of n. So it gives an asymptotic estimate on the tail of the first entrance time in the negative axis of the random walk. So here big L is the slowly varying function involved in the tail of mu, and here Bn is the centering constant. And the probability that the second weak ladder time, or if you want the first ladder time, weak ladder time after time 0 is big, is asymptotic to 1 over lambda of n. And it is really crucial that the same slowly varying function lambda appears in both estimates. So the proof is technical. It starts as usual by using the Wiener-Hopf factorization identity, and our main input here was to find a way to use Dehaene's monotone density theorem. So it's, but I won't enter details. But an important corollary of this is that the probability that x1, the walk makes a big jump, this is asymptotic to probability that zeta is at least n times probability t1 is at least n. because when you multiply these two estimates, the lambdas go away, and you get L of something divided by something, which is exactly the tail of mu. Okay, so now if you want, you can forget everything about random walks, and this will be essentially the only thing we will use in the proof of condensation. Are there any questions on this part of random walks? So if not, let's turn to the proof of theorem 1, first part. So I said W of n to be the path we are interested in. So it's the random walk under a late return in the negative axis. And the goal is to show that this walk looks like it will be always non-negative. It will touch -1 very far away. It will start like that. It will make a big jump, then it will drift, something like that. And why is this useful? Because in the coding of trees by Lukasiewicz paths, the degrees correspond to the jumps. The number of children is jumps plus 1. So if we establish a one big jump principle for this walk, you get this condensation phenomenon for the tree. Here you will read the maximal degree, which will be of order Bn. So n over L1 of n is this Bn. And if you want here, the time at which you make the big jump, it will not be the height of the condensation vertex, it will be its index in the lexicographical order, essentially. Okay. So now the goal is to show a one big jump principle for a conditioned random walk. And here the idea is to find another walk, Zn, which is simple, that is, for which it is simple to show the one big jump principle, and which is close to the initial random walk in the total variation distance sense. So let's define this new walk Zn definition for every j at least equal to 1, conditionally given in equal j minus 1, you do something. So the idea is to use in, the last weak ladder time up to time n of your random walk, to define this new walk Zn. And this walk is defined in 3 parts. First part, before time j. Zn of I before time j is by definition just the random walk which you force to stay non-negative. This is the first part of the new path Zn. Then you make a macroscopic jump. At time j. And then, once you have made your big jump, you evolve like an independent random walk. Here it should be an I. So this is the definition of the new path Zn. So really the key is to use In to define it. So in other words, you first observe In, and once you know In, you construct your path like that. So 3 independent parts conditionally given In. Or if you want this path, we'll make a big jump at a random location, and the law of this random location depends on N. So theorem 5, the total variation distance between these two paths tends to 0. And this is the main thing. Once you have shown this, you show that Zn, whose definition is rather simple, because you decouple what happens before the large jump and after. It's easy to show that Zn, this new random walk, satisfies the one big jump principle. So are there any questions on this? Yes?
Your definition, you can have ladder times after time j. It's not a problem?
So what you do is that, for example, you throw Wn up to time n. You look at you look In, then you forget this W, and you construct a trajectory here, a jump here, and a new trajectory here. But it's not the same W.
In your definition, In will not be the last which ladder time.
Not of Zn.
Yeah, okay, it's not a problem.
No. But to construct it, you use this first drawing of Wn. You do it, you have the last weak ladder here, then you do this process. But I agree that in this new process, In, it's just the moment of the big jump. So the proof. So the idea, first some notation, set mu n to be the law of Wn, mu n to be the law of the new path Zn. So the idea is to show first something. But before that, before showing something, you find a good event Jn such that first mu n concentrates on Gn. Second, when you look at all events, but intersected with the good event, you tend to 0. So here, the idea is to use the fact that the random walk Zn is simple to find a good event. Essentially, it will be the event on which there is a one big jump principle. And then, to control mu n, which is difficult, you only have to control it on the good event where you know that a one big jump takes place. Okay, so this is the idea. So now I will define this good event Gn where this one big jump principle holds, but there is a cutoff involved, so it's a bit subtle. So since In divided by n converges to 0 in probability, we can fix a cutoff sequence xn such that xn is little o of n, and In and probability that In is greater than or equal to xn tends to 0. So since we control In, we can fix this cutoff xn. And then we set Gn to be the event of paths of length n, such there exists a unique time at which you have a one big jump, but not up to time n, up to time xn. So the good event Gn is the event on which you have a one big jump principle, but up to before time xn, which is little o of n. Then star is not too difficult because you have constructed Zn in a decoupled way, and the main difficulty is double star. So for double star, we work with events of the form not just any generic event A, but with events of the form W times A, with W a fixed trajectory, W0, Wn, which is in the good event, and a generic event. This is because we work with the cylinder sigma field. Okay, and so now we can conclude. So first, what is mu n of W times A? What is the probability that our condition random walk for the first n steps exactly takes values little w0, little w1, little wn, and then is in the event A? So here, this is simply the probability that big w's up to time n are equal to little w's up to time n times probability that after time n I am in A, divided by the probability that zeta is at least n. Okay, so this is just by definition. Wn is a random walk conditioned on zeta at least n, and okay. So maybe I realize that okay, maybe I should add that here plus zeta at least n, meaning that okay, sorry, here in R in z plus to the power n, sorry for that, because I want this probability to be non-equal to 0 essentially. Okay, so now second step, what is mu n of W times A? So this depends of the value of In, because everything is constructed conditionally given In, and so here I will have the Zn in W times But what is the probability that In is less than Xn and the ad hoc path is in W times A? So this is the sum, which will be from j equal to 1 to Xn, probability that In is equal to j minus 1. Okay? Then Zn is constructed in the three parts. The part before time j, the part at time j, the part after time j. So what does it give? It gives me the probability that W0, Wj minus 1 is equal to little w of 0, little w of j minus 1. divided by the probability that zeta is at least j times the probability that x1 is equal to wj minus wj x1 at least bn divided by probability that x1 is at least bn. So for the first part, I just say that I use the first line of the definition, here the second line, and then I say that the probability, I simply have the probability that wj, here I started at, okay, wj, sorry, wj plus 1 up to wn. This has to be equal to little w of j, little w of n, and after that, I am in A. So it's a complicated sum, 3 parts, and here the main thing, the main nice thing comes into play is that since little w, this walk, little w0, little wn is in the good event, actually in this sum there's only one term, because for all the j's, in all the j's there's only one which has this big jump. So this complicated sum is only one term, and this will end the proof. There is a unique j between 1 and xn such that little wj minus little wj minus 1 is at least bn, denoted by j of this path w, which is in the good event. The sum is just probability that in is equal to j of w minus 1. And then if you look carefully at what happens, you can remove this for this j, and you just get, if I, let's say write this b, you get exactly b divided by probability that zeta is at least j. Here I'm going a bit fast, but this is really the crucial thing. And now we can conclude, hence, the difference of mu n of little w times a minus mu n of w times a. This is less than the probability that in is big, that is greater than xn, which tends to 0, plus the probability that in is equal to j of w minus 1 times the probability that zeta is at least n, which comes from this, divided by probability that zeta is at least j of w minus 1. Here we use lemma 2 with the time reversal. To say that this term is equal to the probability, this gives, and sorry, this is the problem of going too fast. There is this term here, which I should put here. So here I also have probability that x1 is greater than or equal to bn. Sorry. So now recall that the probability that in is equal to j is the probability that zeta is greater than j times probability that t1 is greater than n minus j. So actually, when you replace this by the expression of lemma 2, this cancels with this, and you get probability that zeta is greater than equal to n divided by you get this. And here you recognize the expression of corollary 4, but without this. So here, since J of W is little o n, actually this convergence tends to 1 uniformly in J between Y and Xn, and this completes the proof. So the idea is really to use an estimate on probabilities to get something bigger on total variation distances. And this has applications in random planar maps in this stable case and the critical point between the dense phase and the dilute phase in stable maps. This is the phase transition Gregory alluded to this morning. So this has connections with CLE4, but I don't have time to speak about it. So sorry for being a bit over time. Thank you.
Exactly in this case, what are those slowing varying functions in the case where you look at the random map? Do you know that?
So what we did, so Loic identified for a precise weight function so this is a specific weight function which gives a critical non-generic map of parameter 3/2. It was first considered by Ambient, Bud, and Marenko. In this case, Loic did some computations which allows to find the asymptotic tail of the corresponding Bienaymé-Galton-Watson measure, and you get exactly this example I gave you. So in this case, the tail of the offspring distribution is this. So, but this is only the tail. So this allows us to identify L1, but not L2 in general. If you want to identify L2, we also need a asymptotic estimate on really the local probability. But this gives us this log n. So this means that if this is a Boltzmann planar map with this weight with parameter at least 2n, then the boundary times log n over n will converge in distribution to j times the circle. So so here the scaling limit of the boundary is simple, but it's little o of n, but so there's something like that going on.
I think we can respond to further questions during the tea break, and thank you.